high, we continue the two-way analysis of variance. So now that we just drop interaction term and go back to the original, the two-way ANOVA, but we think about the unbalanced data or incomplete design. So that means that previously we have xij is equal to mu plus alpha I plus beta j plus epsilon ij. And we assume that there is only one observation for each pair of ij. But here that we don't assume that. And we may have multiple observations, but sometimes that we don't have any observations for the pair. So if the some pairs are missing, then we say that is incomplete. And if number of observations for the pair ij is different, then we say unbalanced. So maybe I would say unbalanced incomplete design. So when the number of measurements of pairs for the treatment is different, we can still fit the model and do ANOVA, but the interpretation of the table, ANOVA table, has to be different, and it should be sequentially. Yeah, so that means okay, so the model that we test the xij is equal to mu plus epsilon ij is against xij is equal to mu plus alpha I plus epsilon ij. And we can test this, but for the second test, we have to test the second hypothesis to the third one. So we have to test the models sequentially. So first 1 versus 2, and second 2 versus 3. And for the balanced ANOVA, the testing for 1 versus 3 is the same as the 2 versus 3. So that was the special situation. But now that we have to strictly the sequential. Yeah, and the exact formula for the sum of squared residuals and so on. So those are omitted in the course, but we discussed later about it in this chapter, and you can see almost everything. Okay, so example. So think about this, the MT car data set. So this is basically the unbalanced data, and we would like to explain the MPG by the number of gears and number of the carburetors. So MPG is the variable, response variable, and the gears, the first factor, and the carburetors, the second factor. Then we can see the summarized table here. Then, okay, so we have the type of carburetor, 1, 2, 3, 4, 6, 8, and the number of gears, the 3, 4, 5. So we have the 3 factors here, and we have 6 factors here, but the number of observations are not complete, some zeros, and also the unbalanced, sometimes 1, sometimes the 3, 4, 5, 2 maybe. So this is unbalanced data. And we can still fit in the same way. So at first, the gear and the carburetors, these 2 variables are recognized as numeric in R. So we have to make it factor first as factor function we can use. Then we regress the MPG on gear and carburetor. Then we get this table. And ANOVA table, the first line that we test if gear is significant. So that means that we test xij is equal to mu plus alpha I epsilon ij against xij is equal to mu plus alpha I plus epsilon ij. So we compare the 1 versus 2. So 1 is null hypothesis and the 2 is alternative hypothesis. Then we have the second line. So this is the xij is equal to mu plus alpha I plus beta j plus epsilon. And this compares the 2 versus 3. And p-values are here. So both are really significant. So gears are at first useful to explain the MPG. And the second line, even we accounted for gear, still the carburetor have additional information to explain the MPG. So that is interpretation of this ANOVA table. So that means if we change the order of this gear and the carburetor, then our result becomes different. So second ANOVA table, so carburetor first, then gear. Then, okay, so anyway, both are significant, but these p-values are different. So carburetor is more significant because we haven't used the information of the gear beforehand. So if you compare this p-value with the previous p-value, actually the p-value gets smaller, maybe about the 1/3 or 1/4. And the second one becomes less significant because sometimes if we accounted for one variable, the another variable is not necessary anymore. For example, to predict the students, the academic success, maybe SAT score is useful if we have no other information. But if we have, for example, the freshman year's grades in college, then usually the SAT isn't that useful information to predict students' academic success in the second or later years. So that means the second variable becomes less significant. So last time that we have very small, 10 to the power -7, but here -6. So p-value gets larger, so less significant. So if we change the order, then the result changes. And we have to interpret this sequentially. So we have to put the variable in your preferred order. Yeah, so we compare this, and that we do test sequentially. And how to calculate this ANOVA table? So basically, that we use the sum of squared residual for these three linear regression models, and that we say that the first one as sum of squared residual for the first one as SSR0, second one as SSR1, and the third one as SSR2. Then what we did is here. So at first, the first line that we subtract the SS0 minus SS1. So SS1 is a larger model, so error is smaller. So that means this SSD gear is positive value. So this is the 483. This is the number that we had in previous table. So this one, 483. And in the same way, the next line is obtained by SS1 minus SS2. So model 2 is larger, so that means the sum of squared residual is smaller. So this again becomes positive. And finally, the residual. So this is the residual squared, the sum of squared deviation for residuals. And this is SSR2, so 217.689. So these are the F value, sorry, not the, so these are the SSD in the ANOVA table here. Okay. And if we change the order of variables, then the numbers will be changed. And the degrees of freedom is the number of category -1, basically. And this 24 is so remaining the number. So we have the 32 observations. So the total of degrees of freedom should be 32 minus 1. 1 means the intercept. So if first one is 2, second one is 5, then this should be 24 because 2 plus 5 plus 24 is 31. Yeah, so in this way that we can calculate the ANOVA table, then everything that you can calculate it. So ANOVA is a special case of linear regression. But since we haven't studied the regression model with multiple predictors, we cannot really explain everything from the chapter 6 material. But after we finish the multiple linear regression in chapter 11, so this is chapter 7 is a special case of chapter 11, linear regression. Yeah, so this is another way to generate the ANOVA table So if you fit the 3 linear models, then we calculate the sum of squared residuals, then we can get these numbers. So exactly, we can replicate the results. So these are the theory for two-way ANOVA. And the Friedman's test. So the two-way ANOVA, they assume that epsilon ij or epsilon ijk is normal 0 sigma square. So what if this assumption isn't correct? Then we have the so-called the Friedman test. And that is a kind of the two-way ANOVA, two-way layout version of the Kruskal-Wallis test. But this is not really heavily used, so that we don't discuss in this course.